So what we want to do today is construct and discover, let's say, the tractor connection. I think discovering is a good way to put it, because I'd like to give you the feeling that you could easily come up with this yourself, which I think is true. So, remember the aim, the sort of broad aim, is to find a conformal analog of the Ricci calculus. So what we recalled yesterday was that on a pseudo-Riemannian manifold, the metric determines the Levi-Civita connection uniquely. Then that, of course, has its curvature. From that, you can make invariants, and you can make invariant operators very easily. So it's a kind of easy calculus. So we want an analog for conformal geometry. So what I want to talk about is the model for conformal geometry. First, because then one sees how this should arise. I'll do the Riemannian signature version. Doing it in other signatures is not a big deal, but drawing the pictures is more complicated. So, to do this, let's take Rn plus 2 and equip it with a Lorentzian signature metric, so -1, just like that. So, and I'll call that H. So this is Lorentzian signature, but the conformal geometry we're going to end up discussing will have Riemannian signature. Okay, so, well, this is going to give us a group around, let's say, SO n plus 1, 1. In fact, I really want to restrict to the time-preserving part of that for a reason that will shortly be obvious. Okay, but anyway, from this this information here, Rn plus 1 with this metric, we get a null cone, of course. So the cone of null vectors. And I'm interested in the future null cone for making life simple. Let me move this board up a little bit. Help my drawing skills. Okay, so what I want you to do now is take the ray projectivization of this future cone. So in other words, each ray generating that cone becomes a point. So then, of course, topologically, what I get, whoops, is something that should be a sphere. Doesn't look very round, does it? Well, it's a conformal sphere. It can be a bit distorted. So here's a sphere that you get by projectivizing that future cone. Okay, so what sort of geometry is on that sphere? Well, one way to explore it is you could take a section of this projectivization. So let's call it tau, say. And that literally takes a section of the cone, so some sort of picks a point out of each of those rays, and then given that section, you can actually pull back the metric. So we think of this, of course, this is just a bilinear form on Rn plus 2, but I also want to think of it as a metric on Rn plus 2 as an affine space. So we have this metric up here, and I can pull back the metric by this section. So I can have tau star of that metric up there, and that determines a metric on the sphere. Okay, and it's easy to check that this has Riemannian signature, so some Riemannian signature on the sphere. Okay, well, of course, if you use standard coordinates and everything, it's not hard to see that if you take the most obvious section here that you actually get the round metric on the sphere. So you can even get the round metric this way. So what happens if you do a different section? So we could So we don't canonically have a section. That's something we're doing. So we could pick another section like that and pull back the metric, and we get some different metric. And, well, given the name of the course, you won't be surprised to know that these are conformally related. So G hat is omega squared G. Okay, so these are just things that are easy to do either explicitly in coordinates, or in fact, you can prove that these will be conformally related just by pure thought. I just don't have time to go through that argument. But anyway, so what you have canonically on the sphere, so these sections are choices we're making, but what you have canonically, of course, is just the equivalence class, the conformal equivalence class of these metrics. So this is a do-it-yourself kit for constructing a conformal geometry. So it's interesting already because it shows that conformal geometries really do arise just in a very natural way. So this, taking the projectivization of this future cone, you get a sphere with a conformal structure, not with a metric. Okay, so with additional structure assumptions, you can make a metric, but without that, you just get a conformal structure. Good. So, well, we have this group, let's call it G. Oops, try that one. I'll just call that G for simplicity. So Gx on the sphere, and of course, this by construction, this is the group preserving this null cone, and so it preserves all the things I've said here. So it must act conformally. So apart from thinking of this as conformal geometry in the way I was talking about yesterday, we could ask, for instance, what are the G invariant differential operators on the sphere? So questions like G invariant operators. So differential operators that intertwine this G action. And so this links to questions in representation theory and so on. Or we can just think of it sort of naively as we were yesterday. We have these conformal rescalings. We want to produce differential operators on the sphere that are invariant under this action by G. Under conformal rescaling. Okay, so you know, wouldn't it be nice if there was a good calculus for finding all those things? And the claim is that there is, and it's just visible in front of us, right? So let's just see that. So to answer questions like this. So okay, so first of all, notice that Rn plus 2, it's a vector space. So in particular, it's an affine space. So Rn plus 2 has its canonical affine structure. Which means, in particular, in Rn plus 2, you know how to parallelly transport vectors. Right? So this is just like the notion that you learned at primary school or whatever about the relationship between vectors and Rn. Okay, so, but let's think of it, because we're differential geometers, rather than just say we know what two vectors being parallel means, this in particular implies that it has an affine connection. It's flat, of course. So it has parallel transport. So a connection. What's more, as I've already said, we can think of this bilinear form as giving us a metric on Rn plus 2, and it's obviously preserved by this parallel transport because it's just a constant. If you wrote it in standard coordinates, it's just constant coefficients. In standard coordinates, this connection is just differentiation with respect to the coordinates, right? So it has a metric preserved by this connection. Okay, so what I want to do now is see what this means down on the sphere. Well, so let's take the tangent bundle to Rn plus 2. So we're thinking of it as an affine manifold now, Rn plus 2, and restrict it to this future null cone. Okay, so we have this vector bundle on the null cone, which is just a restriction of the tangent bundle to Rn plus 2. And now I want to define an equivalence relation on elements in here. Which will say that a vector based at P on the null cone, so some vector here, is similar to some vector V prime at a point P prime if two things happen. So if, let's call this map pi. So if pi of P equals pi of P prime, in other words, P and P prime are in the same null ray, and if VP and VP prime primed are parallel. Parallel according to this affine structure that you have on Rn plus 2. So if these vectors on the same generator are parallel, I want to say they're equivalent. And then I want a quotient. I want to form this thing that I'll call curly t backslash mathcal t to be t Rn plus 2, restricted to this future null cone, mod this equivalence relation. Then T is a vector bundle, obviously rank n plus 2 on the sphere. Well, it's obviously a vector bundle because if you take a section, you can identify it as a vector, as an object, if you like, with its restriction to a section up here. And then it's just the restriction of a vector bundle, so it's a vector bundle. So, so it's certainly a vector bundle on the sphere. Furthermore, the metric descends to a metric on this vector bundle, which I'll also call H. Why is that? Well, I said the metric is parallel, so we're identifying things up and down the fibers which are parallel, so this obviously descends. And then the connection upstairs, let's call this tilde up here just to distinguish it from the tractor connection. So this affine parallel transport we had upstairs also descends because the notion of descending is through being parallel. So this obviously descends to a connection on Sn. Well, you want to make sure it descends to something. You want to make sure it's a connection, but that's easy to check. Okay, so it descends to a connection that I'll just call nabla or nabla T. Okay, so what we have on the sphere, this standard conformal sphere, is that we have this bundle T, which I'll call a tractor bundle. It has a metric, and it has a connection, which I'll sometimes put this T here or sometimes leave it if it's clear by context. And this connection preserves the metric. So you just have that for free, and you can use that to start attacking problems like how to construct G-invariant differential operators and so on. There's still work to do, and I'll come to that in the next lecture in terms of answering questions like that. But before that, let's look a bit at the structure of this bundle, because we want to generalize this to the curved case. So let's look a little bit at what it looks like. So I'll call it a proposition for emphasis. This bundle has a filtration structure, which I'll write like this. So remember, this is the notation for conformal densities of weight 1. This is a notation I'll explain in a second. Tangent bundle to the sphere twisted by densities of weight, conformal densities of weight minus 1, semi-direct sum densities of that weight. Okay, so what's this notation? So let me just, so if you have a vector space V, and you have some sort of quotient space, I don't know, W, and you have a subspace U, then V has this filtration, and I'll write this briefly as V is W semi-direct sum U. And then I'll use the same notation for bundles. Okay, so what this means is that there's some sort of subspace here of this bundle, so that this subspace, with this one, we get a direct sequence like that. So this is there's a projection to this bit, and this is a subspace, but there's also a direct sum in here. So what's saying in this subbundle, there's also a smaller subbundle. Okay? And this is just indicating in the irreducible parts. And the semi-direct sum sign is used because once you split the sequence, it becomes a direct sum. Okay? Okay, so we have the structure. Where is this coming from? Well, this is kind of obvious. First of all, this comes from the tangent space to the n plus, right? So think of how we got this. We took the tangent space to Rn plus 2, but sitting in there, you have the tangent space to the cone itself. And sitting inside the tangent space to the cone, you have the vertical directions. Okay, so this comes from the vertical directions. They sit inside, so they're generated by the Euler vector field. They sit inside the tangent space to the null cone, and then you have the whole thing. Okay, so that's why you get a filtration structure on this. Now, well, perhaps I'll leave that there for a second. Okay, so the only thing perhaps that's not so obvious yet is where these weights come from. So let me just indicate, I'm only doing this briefly because when we construct the tractor bundle in general, we'll do it more sort of carefully. But I'm just trying to quickly, this is in a sense something you can do as a homework exercise. There's nothing, I mean, I'm sure you could all do this yourself, right? So I'm just trying to indicate what's going on roughly. Let's look at if you had some V, which was a section of this tractor bundle, then that corresponds to something, some vector field along the null cone, which is vertical in the which is parallel in the vertical directions. So what about the Lie derivative along the Euler vector field of V tilde? So remember, so the Euler vector field is the thing that's generating the null rays, or in generating the rays away from the origin in Rn plus 2. So it's just xa ddxa in standard coordinates, right? So say if these are the standard coordinates on Rn plus 2. So that's the Euler vector field. Okay, so what happens with the Lie derivative of this? Well, the Lie derivative is just the bracket of the vector fields, and this is So we have this connection up there that's torsion-free. So this affine connection, it's easy to show this nabla tilde is torsion-free. So this is, we can use that connection to compute this thing. So this is that minus the other way around. But if you look at this formula here, this connection in standard coordinates is just the ddx thing. So when we hit this bit, we'll get a Kronecker delta and so on. So this bit here is just minus, it returns v tilde here. Sorry. So this derivative of that thing, because we have the formula. And on the other hand, this one's 0 because v is parallel up the vertical directions. So the Lie derivative vertically of one of these things representing a tractor downstairs is not 0, it's minus 1. And that's where these weights come from, because for vectors which descend to tangent vectors on the sphere, the Lie derivative will be 0. Okay, so, and the rest of the details of the weights, you know, as I say, that can be homework exercise. But I just wanted to give you a rough idea. Okay, so that's all what we have on the spheres. Well, you can say more, of course, but what we want to do is generalize that now to a curve setting. So have a similar sort of situation. I'm just trying to think whether I want to put the board up or clean the board. Usual strategic issue. Okay, let's just put it up. So this is prolongation and the tractor connection. Okay, so just inspired by that, we'll sort of start again. So here's a definition. We'll say that a manifold of dimension at least 3 is Einstein. That's a little g sub naught. So this is Einstein. So the G naught will indicate a sort of special metric, the Einstein one, if its Ricci tensor is just proportional to the metric itself. Okay, so that's what in these lectures Einstein will mean. Okay, well, as everyone here knows, then Bianchi implies that lambda is constant. This, you know, we could have allowed it to be a function, it'll end up being constant anyway. So, okay. So what this means then is G naught is Einstein if and only if the trace-free part of the Schouten tensor for that metric is 0. Because remember, the Schouten tensor is just a trace adjustment of Ricci. So this is just the same statement. There's no extra content here. Now remember, as I was saying yesterday, if you have a metric of any sort, then you can link it to the conformal metric that you have on any conformal manifold. This thing has weight 2 by some sort of section of a positive section of densities, conformal densities of weight 1. I'll just say densities to mean conformal densities, as I said yesterday. Okay, so these things are linked in that way. And remember that when you do that, if you calculate the derivative of this density using the Levi-Ceveda connection of that metric that it corresponds to, then that's 0. Okay, so let me carefully add 0 to this. So I'm going to add 0 in the sense of I'll calculate everything in this special metric. Okay, so I multiplied that by sigma, which is a non-vanishing section because it's positive. And then I added 0 because this derivative kills sigma. Good. Okay, so certainly this is equivalent to that. But remember that this was, everyone did their exercises from yesterday and checked that this was a conformally invariant equation. on densities of weight 1. So if this holds in the metric G0, I'm using the same sigma, then it certainly holds in some other metric in the conformal class. So this is now the scouting for the new one. So this is for any metric in the same conformal class as that Einstein metric. So this, okay, well, let me just continue. Conversely, if you have a solution of this equation, let's call it star, this thing here. So if we have a solution of star, then we can always, go back and calculate in the scale, in the scale that makes sigma vanish. So in other words, if we have a solution of this, you can go back and calculate in the scale sigma to the minus 2 g bar, and then call that G0, and then this term will drop out, and so you'll get the trace-free part of Scoutner 0. So this is a conformally invariant way of describing that, nothing more, okay? So little progress, but we'll see it's kind of useful. Okay, let's even write it as a proposition, even though it's obvious. So there exists an Einstein metric G0 in the conformal class if and only if there exists some positive conformal density such that star holds. Okay, so this is a conformal way of describing an Einstein metric, in other words. Okay, now let me give a definition. I want to say that a conformal manifold equipped with such a scale is, okay, now when I say such a scale, I'm going to change it a little bit, is almost Einstein if sigma, which is not identically 0, but is just a density of weight 1, solves star. Okay, what am I doing here? An Einstein metric is the same as a positive conformal density of weight 1 solving star. I want to drop the positive. I want to allow sigma to have zeros as well, just for fun, okay? So it will be fun, you'll see. But also, this is a linear equation. It doesn't make sense really to if you want to just analyze that equation, it's better to drop that condition and just let sigma be any section of this. And we'll worry later on, especially tomorrow, about what the zero locus of this is and things like that. Okay, so so now I want to study this by prolonging star. Okay, so let's forget our objective for a second and just say we were interested in this equation, which is an overdetermined linear PDE. So there's a thing that you can do with overdetermined linear PDEs called prolonging. And really all it involves is adding extra variables to try to make it into a closed first-order system, except that with PDEs, you have to often differentiate more and so on. So there's sort of representation theory behind this, but I won't go into all that. Okay, so star is equivalent to, well, grad A sigma was is going to be mu. I'm going to call that variable mu. Okay, so I'll make an equation for that. Then the actual star equation will become grad A mu B plus rho AB sigma. This symbol we call rho rather than P often in respect of Penrose, who used to call it the rho tensor. So GAB little rho equals 0. Okay, so this is the same as star because I'm just renaming the derivative of sigma mu, and then there's the other equation, and this rho is absorbing the traces. So I've just absorbed trace. I've just introduced the new variable rho, right? Now, has the system closed up? Well, actually, this is such a simple setting it almost has. The derivative of sigma is given in terms of mu. The derivative of mu is given algebraically in terms of sigma and rho. So well, the thing we don't know is what this is algebraically in terms of the others, right? So we want to do that. All right. So it's almost close, so let's finish the job. So what I do is I differentiate this again. In fact, I want to put the grad sigma back in. So I differentiate that again, and I get grad A, grad B, sigma, plus, I'll move things around a bit. Sorry about that. Whoops. That's a BC, grad A rho. Oops, do I want that? Yeah, no. What's that? Yeah, where's that? Oops. I think I'm still missing something, aren't I? No, that's good enough. Okay. Whoops. Yeah, no, that's good. Okay, because the remember the conformal metric is preserved by any Levi-Civita connection from the class. So I'm just differentiating with respect to some background metric here, remember? So so these are Levi-Civita connections with respect to some background thing. Okay, so I want to get this out. So let's contract it with GAB, and then we'll contract it with GBC. Okay, so when you do this, so we're going to get a Laplacian grad C sigma plus grad C rho plus a divergence of the Scouten. By the way, that's just on the Scouten. So a C sigma plus okay, so that's one equation. And now let's do this again. So now, but I contract with BC, so I get grad A Laplacian sigma plus, and now I get n lots of grad A rho plus BC, so grad AJ sigma plus J grad C sigma equals 0. Okay, anyway, now you see that we're winning because I have n lots of grad rho here and one lot there. So when I take the difference of these, I'm going to get some sort of equation. So this is 1, 2, and 2 minus 1 implies that when the dust settles, right, so I'll let you do this again as homework, but it's not hard. You have to just commute here, use the usual way the curvature turns up, and use the contracted Bianchi identity. So you get grad C of rho minus Scouten CA mu A equals 0. So now the derivative of mu is given algebraically in terms of, a derivative of rho is given algebraically in terms of mu, and the system has closed up. It was a linear equation, so when it closes up linearly. Okay, so let's celebrate with a proposition. So on a conformal manifold, let's fix some metric in the conformal class. Then there's a linear connection which I'm going to call grad sup curly T suggestively on, and then I'm using this calligraphic T again, but this is at the moment dependent on the metric, so I'll put this sort of awkward square brackets around it. This bundle consists of densities of weight 1, direct sum, the cotangent bundle twisted with densities of weight 1, direct sum, densities of weight minus 1. And this connection is given by grad A that on sigma mu rho, this is a section of that direct sum bundle, is equal to, well, it's just a system I just derived over there. So grad A sigma minus mu A, grad A mu B plus rho A B, sigma plus conformal metric A B little rho, and then grad A rho minus Scouten A B mu B. And solutions of star, which I'm going to call the AE equation, because that'll be easier to remember later on than star, right? So this equation I want to call AE for almost Einstein equation. Yep. Say that again? Yeah, right, because you remember in the flat case I had a minus 1 there. But I had the tangent bundle, and that's the cotangent bundle, and I'm raising and lowering with the conformal metric. Yeah, so good point. I was going to mention that anyway. Okay, so solutions of this are equivalent to our one-to-one correspondence with parallel sections. Okay, so let me write down this. Okay. Everything is proved except that this is a linear connection. Okay? I mean, the claim that solutions of this are in one-to-one correspondence with that is just completely obvious. It's just rewriting the system, right? Except I differentiate it once more. So there's nothing to prove there. Is it a linear connection? Well, let's look at it. Okay, so let me cover up all this junk here. This is just the Levi-Civita connection acting on the direct sum bundle. So that's a linear connection. Now I'm adding to it something which is just obviously an endomorphism of the variables taking values in one forms. So I'm adding a contortion type thing that you're allowed to add to connections to get a connection. So it's certainly a linear connection. Well, you know, this is little steps, and you might say, well, that's not much progress. But already it's useful, actually, because, for instance, so this is something one can do with overdetermined PDEs all the time. And you see straight away that this constrains, for instance, the number of solutions. So an example of an immediate application is that a corollary, if you like, is that AE has at most n plus 2 linearly independent solutions. I'm assuming here the manifold's connected. Let's always assume the manifold's connected to avoid silly complications. But well, why is that? So here's this equation, overdetermined PDE. Well, now we say that solutions are in one-to-one correspondence with parallel sections for this thing, but the number of linearly independent parallel vectors that you can have is obviously that the parallel vectors form a vector space which has dimension at most the rank of the bundle. Okay, so that's trivial because the bundle has rank n plus 2. But this is something you get immediately without knowing much about this connection. Okay, now I want to study the conformal properties. Because the main disadvantage so far is that I wanted to do something on conformal geometry. I started off with a nice conformally invariant connection, but I sort of spoiled it a bit by fixing a metric to start calculating. Let's see if we can get out of that. Okay, so at a point, we can solve, it's just at a point that grad tau sigma mu rho equals 0, right? So you just parallelly transport away in all directions away from the point. Then at that one point, you have that all derivatives vanish. So what would happen if you did that? Well, let's look at the formula for the connection. It would certainly imply that mu b was equal to grad b sigma. Okay, because we're just looking at our formula for the connection. We now have a parallel section, at least at a point, so mu is grad of sigma. Similarly, rho is equal to minus 1 on n Laplacian sigma plus j sigma. Okay, because this is 0, therefore you can just trace this to find out what rho is, and that's what you get. Okay, so why did I want to do that? Well, this was all calculating in the metric g. So suppose I do this now in the metric g hat, which is conformally related to g. I want to know how the rho, the sigma, mu, and rho transform. Then, well, first of all, before I do that, this is what we want to do, but let me just say that this implies that the connection determines a canonical operator. So that this connection that we found and the metric determine this operator that I'll call sigma goes to d sigma calculated in the operator is going to be called d really, but we're calculating in the metric g. So it's given by n times sigma, n times grad a sigma, and minus Laplacian sigma plus j sigma. Okay, so somehow this formula for the connection is determining this operator. Now I want to know what happens if I change my mind about the metric and do the whole process again for the hatted metric. Well, then I know how these things transform because these are given by formulae in terms of the Levi-Civita connection, and I know how the Levi-Civita connection transforms and how the scalar curvature transforms. So this implies that sigma hat should just, so it's a density of weight 1, it should be, in the new metric, it'll just be itself again because that's just the thing we're trying to solve in the equation AE. Then mu b hatted, so the one calculated in the new metric, is going to be the old mu b plus epsilon b times sigma. And the new rho hat is going to be the old rho minus epsilon b mu b minus a half sigma epsilon squared. Okay, so because this is telling me the sigma, mu, and rho, and as I say, I just look at how those transform, and it tells me how these things want to transform. And by the way, I meant to say, if you have a section of this bundle that's parallel, what we just showed is that it has to be in the range of this operator. By its construction. Okay, of course, being in the range of the operator is not sufficient for it to be parallel, but it is necessary. Okay, so what we find out is that this bundle with the hatted metric, if you have an element sigma hat, mu hat, and rho hat in here with the hatted metric, then it's some transformation acting on sigma, mu, and rho. And remember, so sigma, mu, and rho were the things that were in here. And the transformation we just derived, so it's 1, 0, 0, epsilon c delta bc, let's say, can be a b0 minus half epsilon squared minus epsilon b, whoops, 1. Okay, so, and what you observe, or you could check if you don't see it immediately, is that this is basically a point-dependent group action. Okay, so if you compose two things like that, you get another thing that looks like that. Okay, so, and therefore, we get an equivalence relation. So it's transitive, but the other bits of the equivalence relation are obvious. So you get an equivalence relation over the equivalence relation between G and G hat. Okay, so we can define things to be equivalent in this way, if they're related in this way, over this equivalence that we have on the conformal manifold. And so therefore, we can define a tractor bundle, an invariant thing, to be the disjoint union over each metric in the conformal class of this bundle defined for the metric G, and then you mod by the equivalence relation. So you mod this package by this equivalence relation. And as I say, this is an equivalence relation over the conformal equivalence relation, so this gives you a bundle over MC. And that's fancy stuff. I think you know what we mean. You know, you pick a metric, it's this, and you pick the other metric in the conformal class, it's that. All right. Okay. Then, now, the way we worked out the conformal transformation was using this formula for the operator. So, tautologically, this definition logically implies that we get a differential operator, which I'll call D, which takes densities of weight 1 into this tractor bundle, and it's just the operator that in a scale is given by that. Okay? Obviously, this becomes a conformally invariant operator because I used that formula to make the rule for how things transformed. So now, given a scale, I'll call it a scale even though it may have 0. So given a section of densities of weight 1, so I'll often call that a scale, we'll call the corresponding tractor that you get by doing 1 on n of this D thing applied to sigma, I'll call that the scale tractor. And you'll see as time goes on why I want to give that a kind of special role, because this is an important object. Okay, so there are some basic pieces. So there's lots more to say. So let's call this thing triple star. I want you to sort of burn that into your mind, that transformation, because this transformation, I mean, in practice, we tend to calculate by picking a metric from the conformal class. How do we identify when things are secretly invariant tractors? Well, we calculate with 2 metrics in the conformal class and check whether things are transforming like that. Okay, so this will be the hallmark of an invariant tractor. So you want to try and remember that. Okay, anyway, let's notice some properties of our new construction. First of all, this transformation, oh, it's just here, sorry, implies that this thing has a composition series, which looks a little bit familiar. It looks very familiar now that we've discussed Jean-Philippe's question. So this is the same composition series that we had in the conformally flat case. Now, I'm going to sometimes use an abstract index notation, which will be, I'll use an uppercase like that. And let's say I'll put this index down here. In some ways, we're defining the dual tractor bundle rather than the tractor bundle. But that won't matter much because we'll soon see the symmetric. Okay, and then let's write XA for the thing that puts densities of weight minus 1 into the tractor bundle. Well, yeah. Okay, so what do I mean? Well, this has this composition series. That's what this formula is telling us. It's telling us of the filtration structure of this bundle. And in particular, it has a subbundle consisting of densities of weight minus 1. So I'm just going to use this symbol big XA to be the homomorphism that puts them in there. And I'm going to call this the canonical tractor. Oops. It's also an important object. It's kind of a soldering object. It's a thing that helps glue the tractor bundle to the structure. So, and by the way, I can think of that as being a section of the tractor bundle itself, except with well, let's use abstract indices, except with weight 1, obviously, because it changes the weight. Okay, so those are some important pieces. Then here's an exercise. We haven't discussed the main thing yet. We wrote down this connection over here, right? Now we've said how things should transform to turn this bundle into an invariant tractor bundle. That connection was written down in a metric, but this descends to a connection on that bundle. So what you do is that you show that this connection that I constructed over there intertwines this transformation formula, i.e., if you form the connection, blah, 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 right? And then you hat it. So you actually compute this with a hatted metric. Then you find that this is equal to 1 epsilon, blah, 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 this formula over there, times the unhatted version. Okay, so remember, this transformation is the hallmark of an invariant tractor. So what you just need to check is that this formula here, when you hat everything, ends up transforming in exactly that way. And that says that the connection descends to the tractor bundle. Okay, so therefore, theorem, we get an invariant connection on the tractor bundle. So this is conformally invariant. And remember, what that means is that it descends to a well-defined thing on the conformal manifold. Okay, all right, well. So there's more structure yet. So there's a metric So here's a proposition. The formula so let's take VA to be some tractor computed in the scale G. So this is some sigma mu rho. I guess it's an A. So if I map this to 2 sigma rho minus plus GAB, this is the conformal metric, mu A, mu B, then this defines by polarization a signature P plus 1, Q plus 1 metric on the tractor bundle. So that's 1. And 2, this is preserved by the tractor connection. Okay, what's the P plus 1, Q plus 1? Well, I'm assuming my underlying conformal structure has signature PQ, right? So if that happens, then this thing defines a metric of that signature. So the proof, well, let's look at 1, for example. So if you take, you hat everything in this formula, so you have 2 sigma hat rho hat plus mu. Okay, so that's my formula. And now I put in that rule of how these transform. Well, sigma hat is sigma, so I have 2 sigma. Rho hat is rho minus epsilon dotted into mu minus a half epsilon squared sigma. And then the other one, so mu hat is mu A plus epsilon A sigma, so that's dotted into itself using the conformal metric. And now you can just see visibly that these things cancel out. So there's 2 lots of sigma with a minus sign, epsilon dot mu, and here I'm going to get an epsilon dot mu times the sigma twice because of the 2 different ways, so they cancel out. Similarly for the squared term, there's 1 minus 1 here and 1 plus 1 there, so this is just equal to 2 sigma rho plus mu A, mu A. So that formula is certainly conformally invariant. And then actually the proof of 2 is not much harder. So you just have to stick in this formula and verify that it's the extra terms cancel out to see that this is preserved by the thing. So that really is an easy exercise. I mean, so you could easily try that. So I'll leave that for you. Okay, so well, the comment on the signature. Sorry to move around to strange bits of the board, but I wanted to keep some formulae visible. So the metric we get after polarization would look like sort of V prime V is sigma prime mu prime rho prime lot of zeros 1 G inverse 1 0 sigma mu rho. And so it's just visible that if the conformal structure has signature PQ, then this thing has signature P plus 1, Q plus 1. Okay, so I think we have everything in our proposition proved. Let's just observe as a little corollary, perhaps it's timely to put it here. Well, it's a corollary. It follows from this. This XA, well, let's say, make it the vector now. So XA, which is HAB, XB. So this is the metric I've just been talking about, but now written in abstract indices. I'm going to use it to raise and lower indices. I'm safe to do that, right? Because it's preserved by the connections. So there's no danger in raising and lowering indices using the tractor metric. So this was this thing that gave me this injection. I'm going to raise the index using the metric. Doesn't really matter for the statement I'm going to make. So this is null, meaning that hxx equals 0. Okay, well, that's just from the formula because in a sense, x looks like 0, 0, 1. So when you look at it in a metric, that's what it looks like. So if you use our formula for the metric, then you see that this is therefore null. And this implies that, by the way, so using that and this formula for the metric, that we get the projection. So x gives the injection here, but it also gives the projection there. So the map from t to here is given by taking v in here and mapping it to h, x, and contracting it with v. So x is this canonical tractor, so it does those injections and projections. So that's one of the reasons it's important. Okay, so I'm out of time for this bit, but I'll stop there and start again after the break. Okay, so there was some questions and comments. So one question, which was a good question because this is, when I've given talks related to this before, this confusion has arisen before. So I started off studying this equation that was a kind of conformal to Einstein equation. So in fact, it's this one here, right? Okay, so this is the conformal to Einstein equation. However, when I write down this, I'm not assuming that we're conformal to Einstein or anything. So if this equation has a solution, then roughly speaking, your conformal structure does admit an Einstein metric, okay? But to come up with this connection, I now study the equation. I don't assume it has any solutions. I simply study the equation, okay? So the only thing I said at one point, you can get a tractor parallel for this connection. So what we end up with just by studying the equation is this connection, which is basically a prolonged system equivalent to the equation. It does not assume that you have a Einstein metric in the conformal class. What is true by construction of this is that if there are parallel sections for this, then almost everywhere it'll turn out there is an Einstein metric in the conformal class. Okay, so we will talk more about that later on. But in the meantime, we have just used the fact that this is a conformally invariant equation. We've prolonged it, derived this equivalent system, and from that we have produced a conformally invariant, well, we've constructed a bundle and we've constructed a conformally invariant connection on that bundle, which happens to be related to this equation. And I don't want to forget that it's related to this equation because that's the main point that I'm going to talk about in part 2. Okay, so the other thing that Sean mentioned that maybe with these things like this canonical tractor, so I said that this gives the injection of this bundle into the tractor bundle because we have this filtration structure. So in terms of this sigma, mu, and rho that I'm always using to denote my typical tractor field in a choice of metric, this map X is just the thing that takes a density of weight minus 1 and puts it in the bottom slot as 0, 0, rho. And if you look at the transformations that are still just barely visible here, you can see that if you had 0, 0 and something in the bottom slot, then it would just get multiplied by the 1 that was there, okay? So that's invariant. And similarly, this thing, I said it also gives the projection to here via the metric. Okay, so this is the map that just takes sigma, mu, and rho and pushes the sigma out. So that's also an invariant map. Okay, good. So I think those are the main questions at the moment. So let's, whoops. Okay, so I didn't quite finish. Let's see. Should I say this now? Okay. Okay, I will anyway. So, okay, so what was going to be a sort of final observation in there was that if lots of things you construct out of the tractors will now have a nice interpretation. So, if you take some metric, some metric G naught in C. Okay, so I'm putting this naught there to indicate it's a sort of one we want to study rather than just a background metric. So that implies that, so this is equivalent to some density, remember, a positive density of weight 1. And then once you have this positive density of weight 1, you can hit it with this D operator that I just constructed and then form the scale tractor. So 1 on n D of sigma naught gives me this corresponding scale tractor. Okay, so, or if I put abstract indices on, it would look like that. Okay, and then this has the property, by the way, that if I contract in with this canonical tractor, I get the density back again. Okay, so these are all kind of equivalent objects, if you like. So here's a question. What is HII? Because we have this tractor metric, and now I've constructed this scale tractor. So this is really a section of the dual tractor bundle, if you like, or the tractor bundle. So I can measure its length using the tractor metric, and this is a genuine function. So it's a section of the trivial bundle. So that should be something nice, right? It should be something to do with the structure. So let's work out what it is. So remember this scale tractor. So I applied D to that. So I have sigma naught in the top slot, 1 on n of that. So if you remember the formula for D, and then it'll be grad A of sigma naught minus Laplacian plus trace of Scouten applied to sigma naught, all divided by n. Okay, so that's what the scale tractor is when I compute in terms of some background metric. Okay, so just in terms of some other metric. So what this is, it's, well, so remember, if we want to compute this formula, well, let me write out how you would do that. So you use the metric to sort of write this as a form tractor, if you like. So you get minus Laplacian plus j sigma naught over n grad A sigma naught. Sigma multiplied into sigma naught grad A sigma naught minus 1 on n Laplacian sigma naught. Okay, so that's how you compute the length of this using the tractor metric. And so what you get, so we're calculating in some background metric, is that this is the inverse tractor metric into computing the length of the derivative of sigma, minus 2 on n sigma Laplacian plus j sigma. Whoops. Okay, so that's what that is. So this is all computed. So these are the Levi-Civita connections for the metric G, which is just some background metric. But now what suppose I use this metric here that actually corresponds to sigma. So if I calculate instead, and this is a conformally invariant thing, so the answer is not going to depend on which metric I use to calculate it in. So I calculate in terms of the metric determined by sigma naught, then the derivative of sigma naught is 0, because it's, as I've said, the Levi-Civita connection of that metric makes the corresponding scale parallel. So these terms are all going to drop out. This Laplacian hitting sigma naught, sorry, that's a sigma naught, is going to drop out. And so what we get is minus 2 on n j sigma naught squared. Okay, a sigma naught there and a sigma naught there. So because all the other terms out. But remember, this, I'm using the conformal metric to raise and lower indices here. So this is minus 2 on n, g, so this is the inverse conformal metric, so AB tracing Scouten. So this is minus 2 on n, sigma to the minus 2, because this is the, sorry, sigma naught to the minus 2, the conformal metric, times g naught, I'm calling it g naught, yeah, g naught AB rho AB. Okay, so it's minus 2 on n j, sorry, sigma to the minus 2 naught j, but really j now not as a density calculated in terms of the metric. So I'll put the g naught there. So, and that sigma to the minus 2 cancels that one there. So what this thing equals in the end is just minus 2 on n j calculated in the metric. So not as a density. So in other words, what the length of this is it's up to a, so this is roughly minus the scalar curvature. So the length of that tractor, apart from a constant, is minus the scalar curvature of the metric in the corresponding scale. Okay, now that will be important to us later on, because while you're on a you know, like a pseudo Riemannian manifold, this looks like an incredibly complicated way to describe the scalar curvature, right? But the point is that this length of this tractor is well defined even when sigma is 0, so the metric's not there. So it tells you how the scalar curvature can extend to, in the end we will see the conformal compactification. Okay, so we'll come back to that. So in the meantime, I want to talk about more obvious things. So let's get back to our sort of stated aim, which was invariants and invariant operators. Okay, well, we've just constructed a conformally invariant connection. Therefore, its curvature is going to be a conformally invariant operator. So this is the tractor curvature. So the conformal structure determines canonically this tractor connection, and this canonically determines its curvature, which I'll denote with a kappa, A, B, C, D, like that. Okay, so it's a two-form taking values in endomorphisms of the standard tractor bundle. So in abstract indices, it'll look like that. And this is given in the obvious way. So in the abstract index notation, you do this. Okay, so this is some standard tractor, so a section of the tractor bundle, and you just compute the commutator of the tractor covariant derivative. I'm not always writing this T on there, so by context, this means the tractor connection actually coupled to the Levi-Civita connection because when I differentiate here, this connection has to know about that one form index, but think of it as a tractor connection. So this gives me K, A, B, C, D, U, D. Okay, so what does this thing look like? Well, it's an easy exercise to compute that. So compute in a scale G. So you just pick a metric from the conformal class to compute it, as is implicit here anyway. And what you find is that if this thing was if this was in a metric, sigma mu rho, as always, then what we get here is 0, 0, 0. That part's easy. Then C, A, B, C. I'll say what that is in a second. Then the Weil curvature, which we mentioned before, C, D, 0. 0 minus C, A, B, D, 0, acting on sigma mu D rho. Okay, so this is the Weyl curvature that we mentioned before. This is the cotton tensor, so CABC is equal to 2 grad A rho B skewed C, like that. So, and this is called, I should say, cotton. I'm giving no citations except to French mathematicians, right? So that's a French guy, I believe. Okay, so what you see straight away is that using classical results, for instance, the tractor connection is flat, is equivalent to that the conformal structure is conformally flat. So in other words, it's locally equivalent to the flat model. Okay, well, there's two ways we can see that. So really, I'm suggesting here we just use the classical result because it's a classical result that in dimensions at least 4, a conformal manifold is locally equivalent to the flat model if and only if the Weyl tensor vanishes. And in dimensions 3, the Weyl tensor vanishes identically because of symmetry conditions, and a structure is conformally flat if and only if the cotton tensor vanishes. So using those classical results, it's now evident that the tractor connection being flat gives you that result. What's that? Oh, sure, yeah. So that's right, by Bianchi. Thank you. In higher dimensions, the Weyl tensor vanishing implies the cotton tensor vanishing. Thanks. It's a good point to point that out. So, but actually you can also use, another way to see that is you can use this canonical tractor to actually, when it's flat, to give you a reconstruction locally of the flat model directly. So you can be more fancy, but I won't do that here. Okay. Let me give you an immediate little application of this. So you can now construct conformal abstractions to a metric G being conformal to Einstein. Okay. So remember that what we've seen in the previous lecture is that a metric G is Einstein is equivalent to this scale tractor being parallel. So you take the corresponding scale that corresponds to the metric, form the scale tractor, then this must be parallel if G is Einstein. Okay, so this is sigma to the minus 2G. So that's what I mean by the corresponding scale. Well, if this is parallel, then it'll kill the tractor curvature. So right? Because if something is parallel, it's killed by the connection. So in particular, the curvature has to annihilate it. But this is some conformally invariant object we've found. So this is giving us a constraint on that conformally invariant object. So here's a kind of trivial proposition that you get out of that. If there exists a point P in your manifold such that the tractor curvature at P has maximal rank, and I'll explain what that means in a second, then there's no Einstein, G in the conformal class. What do I mean by having maximal rank? Well, you might have asked me what's with the zeros, right? I mean, well, or what can we make of it? So this is just a calculation, and you find you get this column of zeros here. But what this column of zeros implies is that the tractor curvature kills this canonical tractor. Okay, because remember the canonical tractor, when you write it in a scale, looks like 0, 0, 1, more or less. So it's just picking up that column. Okay, so this thing never has maximal rank in the sense of this matrix here. But apart from that, that's what I mean by maximal rank. So what I mean is that it'll have maximal rank if its kernel is generated by this canonical tractor. Okay, the kernel in that sense. Does everyone understand what I mean? So, okay, but if that happens, that it has maximal rank in that sense, then there's no Einstein metric in here. And the point is that since if this is a metric, so G Einstein, then that means that that the scale thing that corresponds to the metric is not 0 at P. And therefore, the scale tractor, which I've got written down somewhere probably, no, it's got lost, but it always has something in the top slot. So I equals sigma, blah, blah, and then things down here. So I is not proportional to x. Okay, so if it's an Einstein metric, an actual Einstein metric, it's not proportional to x. So you can only have something parallel if this is not maximal rank in that sense. Okay, well, so what? Well, what you can then do is use this condition to generate conformal invariants to being conformal to Einstein. So that's the thing that was looked at classically. People in the past, wrote papers about, even I've written one, about what are conformal and conformally invariant abstractions to having an Einstein metric in the conformal class. Well, you can now just manufacture such things by starting with the tractor curvature and basically using this condition to produce them. I think that it's a sort of easy exercise. Okay, so okay, but what about we want to manufacture invariants and invariant operators. So and this comes to the point that wasn't sort of explored well in the early to mid parts of last century, because the Cartan connection, as I said, was around in 1923, and Thomas constructed a version of this tractor stuff in one sense in 1926 or so, but people didn't understand how to use it to make invariants and invariant operators. And part of the reason was just this. So we have this connection which sends tractor bundles to one form's tensor tractor bundle. So it's a connection on the tractor bundle. And by the way, I should say, therefore you get a connection on all the tensor powers of the tractor bundle, because in the obvious way, and all tensor parts of tensor powers of the tractor bundle. So you get connections on all the obvious things made out of the tractor bundle. But so if you start off with a tractor, you can differentiate it in a conformally invariant way. That's good. But now this is not a tractor, so not a tractor bundle. So we can't naively iterate the connection and produce, put the jets of tractors into tractor bundles using the invariant connection. So you're sort of stuck. And more or less for this reason, as I understand it, people didn't use the connection for lots of things it could have been used for. Okay, so we want to construct another operator, and we already have made part of the progress. So recall we've made this operator D, which takes densities of weight 1 and invariantly maps them into tractors. All right, this is we call it the Thomas D, if you like. But this generalizes. So proposition, there exists a conformally invariant operator, dA, which takes any tractor bundle of weight W and maps it into tractors, tenths of that tractor bundle of weight W minus 1. So it changes the weight. Okay, so what's this notation here? So I'm using this sort of uppercase Greek index to mean perhaps a collection of tractor indices or whatever. This is some tractor bundles. So this is, so is some tractor bundle in some tensor power of the tractor bundle or its dual or combinations thereof or tensor part of something like that. Okay, so take anything like that, tensor densities of weight W, there's a conformally invariant operator that takes things like that to the standard tractor bundle tensor the bundle you started with, except the weight's shifted by 1, and it's given by this formula, which is almost like the formula we gave before. So here's this thing with all its indices suppressed. So when you calculate in a metric, this is given by this formula here, n plus 2w minus 2, the weight times the thing you started with, n plus 2w minus 2, the derivative with the tractor connection of the thing you started with, and minus the Laplacian plus w times the trace of Scouten acting on that thing. Okay? Now in here, this is the coupled Levi-Civita tractor connection. So I mean, as a first version of understanding this, you should just think, that's the tractor connection in there because it's acting on tractors. But remember, I've put things twisted with a weight, and the tractor connection doesn't know how to act on things with a weight, but the Levi-Civita connection does. So this has to be the coupled Levi-Civita tractor connection. And here, it's even more important because that's the Laplacian, and inside the Laplacian, you have the connection acting on one form's tensor, whatever. So, but anyway, so you write down this formula with that understanding, and then how do you know that this really gives an invariant operator? Well, you go back to that triple star hallmark of an invariant tractor thing. This transforms in the right way, all right? That's why this is an invariant operator. There are other more slick constructions, but they would take us a bit far afield where you construct it more invariantly. But suffice to say that there is this conformally invariant operator. All right. Now, there's quite a lot of content in saying that transforms correctly, as you'll see in a minute. All right. Okay, but look, as a sort of first dumb application, one can now see that you can for most weights, you've solved the problem of constructing invariants of things because you can iterate this and it stays in tractor land, right? It's a happy tractor, happy operator. Unlike the connection, it keeps moving from tractors to tractors. So if you start with let me write it. So application. Invariance of densities and weighted tractors. Okay. Start off with something, right? It's either a density or perhaps it has tractor indices as well that I'm not going to write down. All right? So it's a section of that bundle. You can map this to itself, the section. You can apply D. You can apply D again. And so on. And for most weights, right, one has to be careful when these become 0, but for most weights, like if you pick the weight W equals pi or something like that, these will never be 0, right? So this will package the jets, the Taylor series data of this thing into tractor packages. And then you can contract these things together using the tractor metric and so on and construct invariants of that data. So, so for example, suppose you start off with an actual density. So it's a section of that thing, okay? So let's do the simplest one. So you do DAF, and then you contract it using the tractor metric with itself. Well, you just use this formula, and then you use the formula for the tractor metric to contract it together. And what you find is that this is minus 2w n plus 2w minus 2 f Laplacian f plus wjf plus that number squared. The details don't matter much here, of course. This is not an important example. It's just an example to show you how this works. So this thing on the right-hand side is conformally invariant, right? Now, you could find this by hand by just writing down the stuff as a linear combination and trying to find what numbers you put here to make it conformally invariant. But this is just producing that for you. And it's already clear that this would be quite a calculation to do that, right? So, and similarly, you can, if you did dA, dB, F, dA, dB, F, contracted that with itself, you get some huge lot of numbers out here. N plus 2w minus 4, n plus 2w minus 2, w minus 1, times f Laplacian squared f plus lower order terms. Okay, I'm not going to write it out. But anyway, so you manufacture things quite quickly that are conformally invariant. Okay, so this is, and such things are kind of models for the construction of conformal invariants of the actual structure itself. So I'll come back to that in a minute. All right. Well, what about linear operators? So I think here people are interested in, especially in linear operators. Well, I'm not going to talk about how you make linear operators, conformal operators in general, but what can we make from D? Okay, well, one of people's favorite operators are Laplacian type operators. So you might try this. So you take a density F and you map it to DAF, DAF. Okay, so by construction, this is certainly conformally invariant. And then it has no indices, so it would have to be, if it's not 0, it would have to be a Laplacian type operator. So you might hope that this is a nice construction of some Laplacian type operator. But notice that it would have to be conformally invariant for all weights, because this D operator is conformally invariant for all weights. So this would be a Laplacian type operator which is conformally invariant for all weights. And then if you look using representation theory at what's available in the flat case, there's no such thing, right? So certainly in the flat case, you would guess that this thing has to be 0. And actually, it's true in the curved case as well. Okay, so that's a false lead, if you like, but a useful identity. But on the other hand, let's go back to our formula for D. Notice what happens up here if W is equal to 1 minus n on 2. Okay, so then n plus 2w minus 2 is 0. And so for F in here, we get that DAF equals 0, 0 minus Laplacian plus 1 minus n on 2, J acting on F. Okay, well, those of you that were fairly conscious yesterday will remember that that's the formula for the conformal Laplacian. Of course, by construction, this is conformally invariant, so we had to get something conformally invariant. But even better, this, what we now know is that this even works if this has tractor indices. Okay, so that's what I said. There's quite a lot of content when I say that that thing transforms correctly. One doesn't want to take it too lightly, right? It's easy to think, oh, yeah, okay, you calculate it works. it's not quite so simple. It really does transform correctly, and that shows that this, so we have a consequence, sort of, yeah, lemma, let's call it a lemma. I've got a use for it. So this operator box, which was the conformal Laplacian, actually generalizes to an operator on tractors of weight 1 minus n on 2 to tractors with the same tractor index structure of weight minus 1 minus n on 2. So this is for any tractor bundle. So this is a conformally invariant Laplacian type operator. Well, it's that operator there. Okay. So, well, is that useful? Yeah. So, so here's an exercise. This is a real exercise. It's not a joke one, but it's a little bit of work. But if you're someone who really wants to follow this, it's well worth doing. So. So show that if F is a density of weight 2 minus n on 2, then now I take this box that I've just discovered here. So that's this thing in the bottom slot. Remember calling that box F. I said we can apply this to any tractors, so I apply it to dA of F. Okay, so I apply that tractor D operator, then this twisted conformal Laplacian. Show that that's of the form minus XA P4F. Okay? What I mean is that we get 0, 0 minus P4F. Minus is just a normalization condition. Where P4F equals Laplacian squared F plus lower order terms. Okay, so you just use your formula for the tractor connection in here, apply this to another tractor, calculate, and show that you get 0, 0 something, and therefore this something must be a conformally invariant operator. Therefore, P4 takes densities of 2 minus n on 2 to densities of weight minus 2 minus n on 2 is conformally invariant. So it's a conformally invariant Laplacian square type operator. Okay, this is the Panizzi operator. So the celebrated, so in certain circles, very famous, Panizzi. Discovered in 83, 84, and 86 by different people. So by Panizzi, a physicist named Riemann, and then by Eastwood and Singer, without knowing about each other's work. But so it was all happening in the 80s. They weren't using tractors, and it was a big deal to find things like this because they were calculating the other way, like just by hand. Okay, but this hits it on the head. So that really is the Panizzi operator that comes up. And it's related to this Branson's Q curvature and so on. And that's easy to get out of this. But I won't put, probably it's not something people here know about. Okay, so now, a little warning. So I said this was a density. Overall, over here I said this works for any tractor. So this is false if instead F is in here. Okay, so it works if this is just densities of that weight, and doesn't work that you get this result if it has tractor indices. Okay, so you know, don't think this is all just stupid calculations, because there's quite subtle stuff going on here. And this is if this did work when there were with tractor indices, it would lead to contradictions in mathematics. So it not only doesn't work, if it worked, you would prove the existence of operators that we can prove don't exist, things like that. All right. So yeah, so some subtle things. I won't be able to go into all that. What we say here is that this is not a strongly invariant operator. You cannot twist this Panizzi operator in general especially in particular in dimension 4, but you cannot twist it in the way it's usually given to give an operator which is conformally invariant on tractors. There are very similar operators that you can twist and make operators on tractors, so it gets quite subtle. But anyway, let's stick with the non-subtle stuff. Okay, so because a lot of things are easy. So now, I'm going to slowly get behind, I see. Okay, what about making complicated calculations? I just want to show you that you could calculate anything. And I mean, you can treat a monkey to calculate with tractors easily. So that's really what I want to show you. So, or you can do it while drinking lots of beer or something like that. Even better, you can teach machines to do it. Because monkeys are probably smart and get bored. You know. Okay, so kind of making calculations tractable, haha. So, okay, so have a conformal structure. So, but suppose you pick a metric from the conformal structure, then remember what we've found out is that the tractor bundle decomposes. So there's it's isomorphic to this direct sum bundle. Okay, so, and remember that as we discussed this map here, for instance, this thing we call XA. Now what I want to do is give some labels to the other maps, because now this this map here is conformally invariant, the thing that puts densities of weight -1 in here. These other things, the rest of the splitting depends on the choice of metric. But remember, this was by now I've lost my white chalk. Well, anyway, I'll write in yellow. So, oh, it's not yellow, it just looks it. Okay, so this is sigma, oh yeah, so sigma mu rho goes to UA or something. So we have XA puts these ones in here. And that's conformally invariant. Then I want to name the other projectors. So I write ZAA for the thing that takes the middle slot and puts that into tractors. So this depends on the metric, okay? But I've picked a metric. And then YA takes densities of weight 1 and puts them in the top slot. Again, it depends on the metric. But then I can rewrite my object up there in this form. So I have UA is sigma times YA plus mu A ZAA plus rho XA. So if you like, you can think of the combination of Y, Z, and X as an adapted frame. These are abstract indices, but if I picked, sort of 1 up to n for this bit, underlined it, made it concrete indices, this is just an adapted frame. Nothing complicated. But because it's an adapted frame, there's some nice properties. So we have XA, YA equals 1, ZA, C, Z, B, C equals, whoops, is that the one I wanted? No. ZA, I wanted an AB. This is the Kronecker delta, AB, on the tensors. And all other dot products of these X, Y, Z's are 0. So other contractions are 0. Okay, so in this sort of adapted frame thing, this captures the information about the metric. So HAB is XA, YA plus, YB. So XB, YA plus, plus Z, A, C, Z, B, C. So it's a way of this is the algebraic side of computing this way. And then you need to know how these things transform conformally, but that's easy. So you just read off from the way we know that tractors transform to work out how this adapted frame transforms. So under G maps to G hat equals omega squared G. As usual, we have X A hat. Well, I said this is conformally invariant, so that's that. Z A hat equals Z A plus epsilon A X A. Perhaps I should make that a B, so it's doesn't matter. Okay, and then Y hat A equals YA minus epsilon A B. Okay, so this tells you how those, we call them projectors. So X, Y, and Z are projectors. I don't know if it's a good name or not, but let's just not argue about that. So, but anyway, using that, you can now work out, for instance, the composition series of any other tractor bundle, and really compute with that, with such a bundle. So, for instance, suppose you wanted to take the kth power of the tractor bundle and look at how what its composition series looks like. Well, you can easily see that this is it's k minus 1 forms oops, of weight k. Okay, so this means just k minus 1 forms in the usual sense downstairs, twisted with densities of weight k, semi-direct sum k minus 2 forms of weight k minus 2, sort of direct sum in here, k forms, direct sum, semi-direct sum, k minus 1 forms of weight k minus 2. Okay, so how do you see this composition structure? Well, this part is just sort of this X projector wedged, being in the formal in the way I'm talking about this, but k minus 1z. Okay, so, and you can see that that's invariant because the way this transforms is just by sum of this X. So if you wedge this with 1x, or any number of these with 1x, it kills off the transformation. So this is an invariant thing that puts that in here. Here, this is the wedge k of these, the z part. This is x wedge y wedge some power of the k, so wedge k minus 2 of the z's. And here this is y wedge k minus 1 of the z's. Okay, so anyway, I don't want to go into this in detail. We'll only need this for k equals 2. But you can work out how any sort of tractor bundle, how the composition series looks, and really how to write the projectors for it and so on. Okay, so then if you wanted to compute this way, what you should do is write the tractor connection as an operator on these projectors. And this just corresponds to the usual thing where you capture a connection by how it acts on the frame, by its connection coefficients. Okay, so if you had UB is sigma YB plus mu A ZB A plus rho XB, then how does the connection act on this thing? Well, I gave you the formula for the connection, so let's write that down. So remember, in the top slot, it was grad A, so of sigma minus mu A plus Z, whoops, that should be a mu. Let's make it a B like that. So Z, B, B, and then it was grad A mu b plus rho ab sigma plus gab times little rho. Okay, and then plus xb grad a rho minus dab mu b. Okay, so that was the formula I gave you before for the connection. On the other hand, I can also just differentiate this using the tractor connection and use the Leibniz rule, right? So we should compare this with yb grad a sigma when the derivative hits the sigma plus sigma grad a yb when the derivative hits the y plus and so on. I'll run out of time if I write it, but you just write down the different terms you get, and then you equate coefficients, right? So you equate coefficients of y's and z's and so on. And so you get that, you equate the coefficients of sigma, mu, and rho, actually. So what you get is that the derivative of xb is zba. So this z projector is actually nicely captured as the derivative of x using this coupled Levi-Sever attractor connection. The grad a of the z b is minus Scouten xb minus yb gab, and the derivative of yb is Scouten zb. Get everything. Okay. So these are the transport equations, if you like, for these projectors or for this adapted frame. Okay, so there's an application. Well, first of all, let me show you the application for computing. So the point really is that once you have the connection acting on these, this sort of adapted frame, if you like, you can take any tractor object and write it as in terms of this adapted frame, and then compute the connection just by the Leibniz rule and using these rules. So any calculation becomes just completely algorithmic. There's only those two inputs apart from simplifying. Simplifying is not trivial. As you know, anyone who's done calculations, that's the hard bit. But everything else is easily done with software. But let's develop our own software. But suppose you wanted to compute this. So suppose you have F in here, some tractor bundle of weight W, and you want to compute this tractor D operator acting on XA times F, right? So that means that, right? Suppose you just wanted to compute that using this stuff. Okay, so it's quite easy. So first of all, in here is that Laplacian type term. So let me do that as a first calculation. So first, there's going to be a term that looks like this, plus something J XA F. Well, F has weight W, X has weight 1, so this is weight W plus 1 here. So that'll be a W plus 1. Now, that won't matter much because this is just algebraic and X is null, remember. So when X contracts into itself, you get 0. So this is going to be equal to XA Laplacian XAF, where we used, as I say, that XA equals 0. Okay, now we use this again. So this is equal to XA and then the commutator bracket of those things, because when the X hits the X, you get 0. So now we can split this up into grad B. This is just the usual Laplacian. So XA F plus XA grad B, XA grad B F. Okay, so just breaking up this commutator bracket in the usual way. Now, when this hits that, I get a Z. So this is a XA grad B. So this is first order, so this is just like that acting on that. So I get a Z, what the order to have it in? BA maybe? AB, I forget. Anyway, it doesn't matter. Okay, so it's one of those times F. It's acting on all of that, but when the derivative hits the F, the Z will hit the X, and that gives 0, remember? So in fact, the only term that's going to survive is that one. Plus, and then I get, so I get another one of these Z's here, but it's killed by that. So this is the surviving term, and using my formulae over here, this is XA minus J XA minus NYA. So I had to trace the formulae over there because I've got this contracted in. So times F, and then the X kills the X, so the only term that survives is minus NF. All right. So now I'm ready. So that was my preliminary calculation. Okay, so, yikes. I wanted to do that. Well, this is going to be, well, this is weight W, so this is weight W plus 1. So I use my formula for that thing. So it's a W plus 1 now, N plus 2W minus 2 plus 2, so N plus 2W, YA plus N plus 2W, same argument, times ZAA grad A minus XA, and then this calculation we just did. Oops, it's XAF, isn't it? All right. Okay, well, this Y just picks up 1 here. So I get a W plus 1, N plus 2W times F plus, yeah, what do I want to do here? So, oh yeah, so this derivative hits that and makes another Z. Otherwise, the X kills the thing. So I get plus N plus 2W ZAA ZAA. And then I have my calculation from over there that gives me an NF because of the minus sign. And now this, of course, is, whoops, that's times F. This is just N because of the relations between the Z's. And so when I put this all together, I get dA XAF equals N plus 2W plus 2 N plus WF, okay? So the purpose of that is to show you, firstly, how to calculate, just using, kind of calculate now like an idiot. You just keep using these rules, right? So there's nothing to do. But here's an immediate application that's already quite interesting. So theorem on a conformal manifold for any tractor bundle and K a positive, positive integer, if the dimension is odd, or if the dimension is even, we'll insist that 2K is less than N, if N is even. There exists a conformally invariant operator, box 2K, which sends tractors of that weight, K minus N on 2, to tractors twisted with minus K minus N on 2, which is of the form Laplacian to the K plus lower order terms. So they're kind of higher order analogs of this Panizzi operator with those restrictions. So what's the proof of that? Because this is something, as I say, so in the mid-80s, they were up to making a Laplacian squared operator, and the technology that was being used back then wouldn't have gone any further. There's a construction of conformal Laplacian operators due to Graham, Jen, Mason, and Sparling that uses a thing called the Pfefferman-Graham construction that broke that impasse. But here's an easy way to make Laplacian-type operators using this machinery. This is given by dA1 applied to dA2, let's say, and so on, dAk minus 1. Now you use this operator we constructed before, this twisted conformal Laplacian, dAk minus 1, and unwrap it the same way applied to F. Okay, so you just apply a lot of these tractor D operators, apply that twisted Laplacian operator, and then take off the indices using more of these. And the reason that you know you get something non-zero is you repeatedly use this to pick off the highest order term. And you can see that given this thing here, because the leading term of this bit, it's easy to see from the formula for the tractor derivative, is some minus 1 to some sign, and then xa1 up to xak minus 1 times Laplacian to the kf plus. Okay, so that's just immediate from the formula for the tractor D operator. So to get the leading term, you just have to know how these D's take this off and not interfere with other parts to produce terms of that order, which you can prove by induction. But it's easy induction. The main content, as I say, is just this identity here. Okay, so okay, maybe just let me just say a final remark on curvature because it won't fit into the next lecture. Sorry to run over time slightly. So that's invariant operators. You can also proliferate invariants now. Okay, so you can form this thing, WABKL, which is defined to be equal to 3 over n minus 2 dp. This is this tractor D operator. Then this fundamental tractor X skewed with the Z's, A, B, Z, B, B, contracted into the tractor curvature, A, B, K, L. Okay, so, let's look at that. This is conformally invariant. That's the curvature of the tractor connection. These things depend on the metric, but when you skew with X, this becomes conformally invariant. And then this is conformally invariant. So you can form this object, and this is a kind of higher order curvature thing. So this has an n minus 4, and then it has parts containing the Weil curvature, and it has parts containing cotton, and then it has a part which is the Bach tensor. So if I had more time, I'd explain in detail. But so now using this thing we call the W tractor, you can map it to itself, D of itself, DD of itself, and so on, just like we mentioned for densities. And so you can now take contractions of these things and so on using the tractor metric and produce conformal invariants of the structure, because everything now by construction is conformally invariant. For n odd, all invariants, conformal invariants, arise from this. Okay, so let me just say in words what I mean. So you make Weil type constructions, but using tractors now. So Weil invariant type constructions where you contract these things together in the obvious way. You take d derivatives of this W, and that construction in odd dimensions, all conformal invariants of the structure are generated by such things. In even dimensions, this makes some, And it's a lot more complicated finishing the story because it's not finished. As I said, there's open problems related to that. Okay, I'll stop there.